Hi everybody, I'm gonna make this video in Zoom. I'm really here. I'm gonna turn my camera off since it's too much to focus on flipping between screens and looking at myself. But using Zoom because we're gonna be going through some slides and using an applet in Geogebra to help illustrate and look at the graphs of solutions, the systems of differential equations. So you can find the link to that Geogebra app in Canvas. You might wanna open up that website. You can see the link over here in the slides as well. So I'm going to turn off the camera and just kind of navigate us through this example. The goal here is going to be to see how we can get graphical approximations for systems of differential equations. So, with one differential equation, we could use the slope fields to essentially graph Euler's method and look at the estimates. And so now we're going to go ahead and graph the estimates that we got in the previous video where we used Euler's method for this same system of differential equations. So over here, we're looking at the system of interacting populations between rabbits and foxes over time t. And so we came up with some estimates if we had initial condition of 300 rabbits and 20 foxes. The previous video, we went through Euler's method to see what our prediction would be 1 year from now. And so in order to visualize this, now we've got three variables, R, F, and T. So this is gonna look like graphs a little more like in the XYZ three-dimensional coordinate system. So this is why we're gonna use Geogebra Applet, which is gonna help us with an interactive version of that. So I am gonna jump into sharing my Geogebra screen over here. Okay, so now you're looking at this website, Geogebra, and so this was, you can see the author of this Geogebra page. This is a really nice applet, so shout out to the IOD people who developed this. So what we're looking at here is our three-dimensional system. So we have F axis and R axis and a T axis. And we're gonna start with initially R is equal to 3, so we've got 300 rabbits. F is 2, so we have 20 foxes. And here, let's run Euler's method to generate the approximations. It's going to create a table for us. The difference is they used step sizes of delta t being 0.1, whereas in our previous video, to make the calculations a little more manageable, we used 0.5. And here you can see they got slightly different, they got different estimates than we got in our previous video because they used smaller step sizes. And so let's take a look at what these solutions might look like. And so what's going on here is it's just plotting each of those individual points and sort of connecting them with a curve. And so what we can see is we get some sort of cyclic behavior between these two populations. So there's another option to use what's called a different numerical method called the Runge-Kutta Method, which is pretty similar to Euler's method. It just makes some refinements to get it slightly more accurate. And so let's run the approximation using Runge-Kutta, and you can see we get a slightly different approximation. And if we animate these solutions, we get a similar looking curve, but this is going to be a better approximation than the previous picture that we had with Euler's method. And so now we've got the system in kind of like our XYZ plane. And so this is telling us how all three of these things interact with each other, and it's a little bit more complicated. So what's nice about this graph is we can drag it around and change our angle of perspective. So essentially, if you think back to multivariable calculus, you may recall looking at cross sections and projections of things in three-dimensional space into a two-dimensional coordinate plane. So for example, if I just want to see how is the rabbit population changing with time, I can drag this around, and now I've got a graph. Ignoring the foxes for now, we can see how the rabbit population is changing with time. In particular, it looks like we have some sort of trigonometric behavior here, sinusoidal function. And what it looks like is our rabbits are starting off at 3, and it's going down, and then it's going back up, and it's going back down. And the reason why it goes up and down, it's because of the foxes that are over here. And so if you spin this around, then we can look at the relationship between foxes and time, and we can see it also is of some cyclic nature. And maybe at the end of the day, we might be interested in thinking about how are the rabbits and foxes themselves interacting with each other, and we get this little cyclical graph over here. So you can twist these axes around, and it's quite nice to play around with this. And you can change the initial conditions as well. But I'm gonna switch back over to the slides to try and work through what these graphs are actually telling us. So let me change back over to my iPad. Okay, so let's start. Here's a picture of the graph of R versus T. And so let me zoom in on this a little bit. So here's our graph that we saw before. And yeah, so this is telling us the cyclic nature of the rabbit population. So we've got R versus T. And if you were to look at this graph, it seems like we have some sort of cosine function because it's starting off at its maximum value over here. So maybe a good guess, even without solving this, we can see that it would be reasonable to suspect some cosine function where we've adjusted the period, the amplitude, and the midline. And looking over at the view where we were comparing F versus T, now we can see that the fox population is going up and down, and this is relating to how the foxes and the rabbits are interacting with each other. And looking at that formula, it also is sinusoidal. Maybe it's more reasonable here to start with a sine function because the graph of F versus T starts on its midline. So maybe we have some other constant sine of omega T plus some other constant D over here. So we've played around with the amplitude period at midline of that one as well. But ultimately, what we're interested in thinking about is how are the rabbits and foxes interacting with each other. And so for that, it would be really nice to look at the graph of just foxes and rabbits. And so here we get a nice kind of oval pattern. And maybe this makes sense if you've thought about how these cyclic populations behave cyclically in nature. And we've got our two equations, or suspected equations, for R and F. So these are like parametric equations for R and F. And if we graph them in the RF plane, it makes some sense why we're getting this cyclic behavior. These coefficients, the B and the D, are telling us really where the center of this is. And these coefficients, A and C, are telling us the kind of the lengths of the major and the minor axes of this oval trajectory that we're getting. So let's take a look at what this graph that we get for R and F is actually telling us. So what we're seeing is, at first, what's happening is we're starting here, and the rabbit population is going down because we're moving to the left, and the fox population starts going up initially. And so as we're moving along this piece of the curve, what's happening is that there's a lot of rabbits, there's not many foxes, so the fox population is going up because they've got a good food supply. But then at some point, say about here, the fox population has gotten so large and the rabbit population has gone down so much that there's too much competition for limited resources. And so what happens now is the fox population goes down, the fox population goes down. And as the fox population is going down, that's actually good for the rabbits, because as their predators go down, they're going to increase their population, and then we get back to where we started, and that's why we get this cyclic nature. So when there's a lot of rabbits present, that's good for the foxes. They grow, but then their population gets too big and the rabbits can't sustain them, so the foxes go down. And as the predators go down, that's good for the rabbits. Their population goes up, then there's enough food supply for the foxes, and this continues on and on. Okay, let me pause here for a second. Okay, hello again. So let's take a look at this applet again. So that was really nice. I think that's a really nice applet, this Geogebra applet, to play around with the dynamics of this system, because we have some good intuition about how we might suspect these populations would interact, and that hopefully makes the math a little more understandable. So let's take a look at a system like on this slide, same system, rabbits and foxes interacting over time. But now we're going to change the initial condition so that at time 0, we've got R is 3. So we have 300 rabbits, but there are no foxes. So let's kind of check first our intuition about what we think might be happening here. And so what we can see is that if the rabbit population, if the fox population were 0, well, what would you expect if there's no predators for the rabbits? Their population should increase, right? That makes sense. And we see that again reflected in this differential equation, that if we had no foxes, then this term would not be around, and the RDT would just be given by this piece of the equation, and that's positive, so we see the rabbit population would go up. And what would happen to the fox population, coincidentally? Well, if f is equal to 0, then what we see is the FDT would equal 0. So that fox population's rate of change is 0. So if you start with no foxes, then you're going to continue to have no foxes. They're not going to spontaneously appear. So that's what the equations are telling us, and that matches what our intuition is telling us. And if we wanted to play around with, I'm going to jump back to this app, this Geogebra app. We could change the initial conditions here to say, well, what if we had no predators, but we had 3 prey? Let's run a simulation approximation of Runge-Kutta on this, and let's see what happens. And you can see here, what's happening is, yeah, this is going up very sharply. And so in fact, we would expect to have exponential growth for the rabbits over time. The foxes, we can't really see their graph because as time goes on, there are no foxes, and we're going to continue to have no foxes. And so then we can kind of move around this and check out the dynamics in the RF plane. And here, all we're seeing is that the rabbit population is shooting up along this axis, but the fox population is 0. So that's why we're just getting a series of dots that run along the R axis. Okay, so feel free to play around with this applet. And I'm going to make one more video relating to the next slide.